Hi, everyone. Welcome to today's research talk. Our speaker today is Aniket Kate. Aniket is an associate professor in the computer science department at Purdue University. He's an applied cryptographer and a privacy researcher. His research builds on and expands applied cryptography, distributed computing, and data-driven analysis to solve security and privacy problems in decentralized environments. His current projects focus on communication freedom and distributed ledgers. He is the recipient of the NSF Career Award for 2019. And before joining Purdue, 2015, he was a junior faculty member at Saarland University in Germany. He completed his postdoctoral fellowship at Max Planck Institute for Software Systems, his PhD at the University of Waterloo, and his master's at the Indian Institute of Technology in Bombay. His talk today is Randpiper, Reconfiguration-Friendly Random Beacons with Quadratic Communication. Professor Kate, thanks so much for joining us. I will turn it over to you and let you take it from here.
So hello, everybody. Thanks for the introduction and also inviting me to give this talk. I'm going to talk about reconfiguration-friendly random beacons. This reconfiguration-friendly is the term that we introduced in this space, and we'll try to understand how to build such beacons protocols. And as the talk title mentioned, indeed, the focus is on the quadratic communication complex. Let's continue. So when we look at the random beacons, what I mean by that is we want to make sure that we publicly emit a random value. And typically for such a random value, we want two properties. We want bias resistance so that it should not be possible for some entity to influence the future random values and take advantage from that. And we want unpredictability, that it should not be possible for somebody to predict the value that's going to get emitted in the future. And such randomness beacons are talked about quite a lot. They have enormous applications, just starting with very simple things as electronic voting and lotteries. But in the blockchain space, many other protocols do indeed require public randomness, and that could be a very useful tool. Typically, we can not assume that just one party somehow generates randomness and publishes it, because that becomes a single point of failure, that when that party goes down, we will not have access to the randomness. And also becomes an escrow problem, because that party now can control and change randomness, which will affect both the bias resistance as well as the unpredictability in general. So what we do in such an environment is we go for typically distributed randomness beacons. So where the idea will be, rather than relying on one party, we'll rely on n parties and then assume that, let's say, a subset of those can actually get compromised. But even against compromisation of a subset of parties, where this compromisation could be crashes or as well as malicious failures, we want to make sure that we maintain the bias resistance and predictability property that we already mentioned, as well as maybe we want to make sure that we achieve optimal resilience in terms of we can tolerate as many faults as we will like. Ideally, we want to go to the level of n-1, but in many times we have to settle on n divided by 2. And we want lower communication overhead. Essentially, such randomness beacon protocol, if it involves communication between parties, we want to make sure that we reduce it as much as we can. We also want to make sure that it is reconfiguration friendly. What I mean by that is that if my protocol requires significant effort when a new node joins, or when we want to throw an old, possibly dysfunctioning node, and if that process is significantly costly, then we will not call such a protocol as a reconfiguration friendly. Instead, we want a protocol where we can seamlessly add and remove nodes from the system. That's what we aim for in system. It's a property which we think is an important property in general distributed systems, which is at times is ignored, not always, but at times is ignored. And we see that that could be important requirement in a randomness beacon protocol that is running for months or years, that we need to change the nodes, and how to do that in an efficient is an important aspect that we observe. And if possible, we like to avoid using expensive schemes such as time commitment and verifiable delay functions. They have their own advantages, but at least our approaches, we don't want to go in that direction and try to employ those to possibly get advantages. We want to avoid using those because they can indeed from our way of thinking, they can indeed introduce performance bottleneck that we are only generating beacons significantly slowly in presence of such a system. So here is a relevant literature that you can also find in the paper if you search for paper with this name. I'll try to focus on some prominent examples in this. And as you can see here, we are typically aiming for quadratic communication complexity in the best case and worst case scenario, if possible. And in fact, in a recent upcoming result, we show that that is a lower bound, at least for most common settings. And in particular, the prominent example here is DRAN, where Protocol Lab, as well as I assume some DRAN people are also involved in this talk, where the idea is that we will assume some kind of a threshold distributed key generation setup for possibly BLS signatures, or for that matter, many other unique signatures that can be possible. And then idea will be, given such a threshold signature setup, we are going to exchange the message that which are basically signed shares of signatures. You combine it together where the signature is generated on a known message or tag, and that uniqueness property which is employed to generate randomness. And typically this involves O of n square communication. However, the reason why we put a reusable setup here in terms of cross, because indeed, whenever we want to actually add a new node or remove a node, we have to change the setup by itself inherently. And I'll come to the cost regarding that very soon. There are also other interesting proposals that have come up working both synchronous setting or partial synchronous or asynchronous setting. But then when we come across, we indeed see a gap there where we want such a reconfiguration friendly setup, and such a protocol doesn't exist. And in this paper, we offer protocols, in particular two protocols, who at least in the best case provide the communication complexity, which is O of n square. Indeed, when adversary behaves maliciously, the complexity increases, which also something I'll visit and talk about later. Do I need to talk about anything else? Yeah, a precursor to us, maybe Hydrant is one of the prominent protocol which offers the quadratic communication complexity in the synchronous setting. However, they indeed go for the 1/3 resiliency, which is not optimal for the synchronous setting that they work. Again, I'll be talking about that, but our focus will be on the synchronous setting for this talk. Okay, so when we look at this DRAN setup, I talked about this concept called distributed key generation. And what does it stand for? And my aim here will be to kind of give a pictorial representation to make the idea clear. So
let me just quickly interrupt. I saw a hand for a question, and I want to invite that person to jump in.
Yeah, that was me. Just a question on the table before. What do you mean by reusable setup?
So by reusable setup, we mean that we have a setup that's ready, and even when we change the settings so that we add the new nodes or remove the nodes, that we can use that without any without updating such a setup. So a particular example for DKG that I'll try to explain that example with DRAN, and probably then it will become clear about it. Okay. So what happens in a distributed key generation beacon protocol is that you are inherently running a distributed key generation protocol for your threshold signature. And to run such a protocol, the idea will be we have nodes who generate secrets. They are generally, they can be parts of either a finite field scalar, or using PVSS scheme, then it can be part of the group elements. And then idea will be every node works as a dealer and provides such secrets and send the shares to others. And that I'm showing here with the two nodes. It's important that such a protocol is run by multiple nodes. Otherwise, the node that generated, let's say, secret one becomes a single point of failure. And then idea will be such a protocol is run by at least T+1, where T is the threshold that we associate in terms of the adversary threshold. And typically we use verifiable secret sharing schemes, and if that has homomorphic properties, we can basically just take our different shares and sum them up and that will result into share of the secret, that is the summation of the secret. We'll have to also include public keys that get generated with that, which I'm not showing you over here, but certainly such an approach is possible. But conceptually, the idea is that multiple parties run secret sharing, in particular verifiable secret sharing, and then we homomorphically combine those shares to obtain the shares for the final secret, which is random and unknown to everyone. Once we have such a setup ready, then idea will be we use such shares to sign well-defined messages, which could be just tag or simply counters, and send those values to each other or the client that are interested. And this process typically will be involve quadratic communication by itself, where we send these shares to each other, and we take these threshold shares and again homomorphically combine them using Lagrange interpolation or different ideas to obtain our final signature on that tag, which if it is a unique signature, could have the property that we required from the randomness, and that's how we generate the random beacons. And the idea will be for every such round or epoch, we generate such shares and continue the protocol to finishing time. Now, if you look at such a setup, that the DKG setup that I mentioned, when I want to, let's say, add a new node, let's say node 5, that becomes inherently a challenging task, because such a node 5 will be now, to incorporate such node part, we have to run the DKG setup again, and then only we can just start using the system again to make sure that it functions. And every time we add or remove node, such a process has to be completed. And I'll talk about the statement later, but typically if we do not assume, make other assumptions, current known protocols to do such a system could easily be actually 10⁴, which is quadric, not even cubic. And that's certainly the challenge in general that we have to deal with for such a DKG setup, which result us into reconsidering the problem, especially if you want to deal with the scenario where nodes maybe change at least intermittently, if not very frequently. If you consider a scenario, envision a scenario where we want to very regularly change the nodes, it can be significantly problematic, assuming such a distributed key generation. There's an inherent point I want to mention here before I move on, that if you look at this process, this is random beacon system in general is a very pipeline process, in the sense that this is not just one shot thing that you run it once and don't run it again. You continuously run such a process. And this is certainly something that we are going to employ towards solving the problem with reconfigurability. And I'll revisit that, but I wanted you to hold that thought in your mind. Moving on, so we saw that where the challenge lies in general, and now we'll try to just understand this problem a bit more conceptually. So as I already mentioned, we are working in bounded synchrony assumption setting. So for this talk purpose, we are going to assume that nodes run in rounds, and that those rounds are bounded by well-known time delta. And when a particular node is supposed to send message to you within this time-bound delta, and if they do not send such a message, then you can assume that such nodes are crashed, or in simplicity, they are malicious, and you can put them in one of your T nodes that are misbehaving in general. In particular, this setting, we will be assumed that all the honest nodes are moving at the clock, are working with the clocks which are moving the same speed, and minor delays can be taken care of, but using better and better NTV protocol that are coming up, we assume that this assumption is certainly becoming more and more practical, even to the level of microseconds. And we also assume that the nodes start executing protocol within the delta time for each other. This can be taken care of what is known as the synchronization protocols. And there are a couple of examples which is already available, and we also include such examples in our paper. So in such a bounded synchronous assumption setting, many of the distributed systems protocol can work tolerating up to n divided by 2, that is up to 49% false. State machine replication, Byzantine broadcast are kind of example for that. But also relevant to our discussion, verifiable secret sharing, distributed key generation, all of them can also work tolerating up to n divided by 2 false in such a setting. However, when we look at many of the distributed key generation protocols or VSS protocols that consider in the literature for significant time, and this also includes many of the multi-party computation protocols. So whenever those protocols considered typically in the literature, they always, along with the synchrony, they also assume access to a round-based broadcast channel so that those broadcast channels finish broadcasting message to the nodes within that time period. At times, those broadcast channels are replaced by the term bulletin board, but they still exist. And when we look at this broadcast channel, it actually means that when a party sends message on such a broadcast channel, that message arrives at all party within a span of single round, and that is visible to every party. So now when I see a message on broadcast channel, I know that all other parties will also see that message on broadcast channel. Is an assumption that's implied. But when we try to actually replace this broadcast channel simplification, abstraction by a real protocol, we come across very interesting challenges. The first one is that inherently, if we replace that by a primitive which precisely implement that, which becomes Byzantine broadcast protocols or BB protocols, then the communication complexity for them is NQ. And some of you might get confused that you might have seen number O of n square there for many protocols, but this n cube is assuming that we do not have access to threshold signature. Because if we have access to the threshold signature, then in first place, we'll just employ them as with the DRAND or such protocols to just generate a random beacon. We don't require to run a separate protocol for that. So inherently in this work or this line of work, the idea will be that we'll not assume any threshold signature or any threshold setup available to us. But we will be assuming standard PKI, assuming that the nodes links keys are known before the protocol start. The public keys are known. That we'll assume in such a setting. But not only the thing is, it's theoretically challenging. In practice, also, oftentimes such broadcast channels are often incorrectly implemented, and we come across such examples like that, or left as a future improvement with possible warnings as well. And for example, DRAN indeed include a complete page talking about interesting issues to deal with the broadcast channel. But that certainly shows that it's a thing which often may not be immediately and practically available to be employed, and that's where we come in picture. I also want to add aspect that assuming standard PKI model, even when we send larger strings over such broadcast channels in theory and use extension technique as our name, so still we'll give O of n cube in total because of the standard PKI setting that is present. Okay, so what we want to solve here is that we want to design an optimally resilient random beacon protocol. That means we want to tolerate up to n divided by 2 faults, and we want to achieve that with O of n square communication complexity. In complete talk, I do not include the security parameter like kappa or lambda in my complete measure, but they are there, and it's always univariate. So that's the reason for simplicity I did not include in my discussion. And while doing that, I want to make sure that I use an efficient cryptographic setup to do it and avoid using threshold signature, as I mentioned. However, to get the efficiency, we indeed use what we call as a reusable setup. And in particular, that's a setup for which I'll be explaining in detail, which is relevant for the QSDF assumption, if you're aware. But before going into the detail regarding that, there's a key thing I wanted to mention here. So we saw already, you run a DKG and then you generate threshold signing by communicating. But then inherently, because randomness becomes a continuous process, maybe we could possibly employ state machine replication, which is again a continuous process than the BV protocol. And then question could be, can we somehow get some progress, some benefit from such a process is an interesting question to ask. However, existing SMR protocols, the state machine replication protocols, such as sync hotstub, opsync, again, are O of n cube in the standard PKI model. Again, for all these protocols, we see O of n square. In the papers, we'll see assuming threshold setup, but which we are not going to assume. So indeed, there is a challenge to solve over here. But the question is that because we are assuming pipelining approach, and then taking kind of motivation from hot stuff, which actually started with a O of n square protocol, at least in the partial synchronous setting, and come up with a O of n protocol using pipelining. Maybe we can come with a protocol for state machine replication, which is O of n square, and that could become a nice step for our problem that we want to solve. So here is how our high-level approach will be. So we are going to assume that users run VSS, that is verifiable secret sharing, or PVSS, that is publicly verifiable secret sharing, to privately commit to the random numbers ahead of time. And because they are committing to them using VSS or PVSS, in the future, those parties by themselves or any honest set of parties could, in principle, reconstruct such a secret. Because parties already committing to their values and they cannot actually change those values, this ensures the bias resistance that is required for the random numbers. And towards ensuring that we have unpredictability, the idea is that we do not use actually input only from one node to generate a randomness secret, but in fact, we employ the input from T+1 nodes such that at least one of them is coming from one honest party. And that's the way we hope to make sure that we have unpredictability guarantee. What I mean by that should become clear soon. That how we combine these things. And there are two different approaches that we employ towards combining setting. So here is one slide in terms of what to expect from this effort. And we indeed work towards a synchronous state machine replication protocol, which is O of n square communication complexity without requiring threshold signing, threshold encryption, and distributed key generation setup. But we indeed rely on a QHDS kind of setup, which is a universal structured reference string, where idea is that you generate such a string which could be significantly longer than your total values and that's required and could be reused by anybody. You can take it string from somebody and update it. So all those things are possible. And such a universal string is what we assume to so that we can get efficiency in terms of the communication. And such a setting, then we provide two RAND protocol. One we call as GRAND Piper. It's a protocol that employs a PVSS, or publicly verifiable secret sharing, and it actually provides O of n square communication complexity. But it allows an adaptive adversary to possibly predict a value for T+1 epoch in future. And the probability of such an adversary is small, but still non-negligible. And that's the reason we also come up with another protocol where we shift from the publicly verifiable secret sharing to verifiable secret sharing and get a protocol which offers unpredictability for every value, even against an adaptive adversary. But with a catch that now our communication complexity increases to Fn square, where F is the actual fault. So this protocol, when there are no fault, behaves in O of n square. And we also include how to actually include new players and remove the players from the system as we make progress through the system, while still making sure that such a transitions happen in an efficient manner while maintaining the quadratic communication complexity of the whole. All right, so let's dive a little bit into the construction to understand what's happening in such a setting. So I'm not going to explain the state machine replication protocol in detail, but I'll kind of set up the boundary for that so that then we can talk about the cryptographic aspects in a bit more detail, given the restriction of the talk. But I'll be happy to talk about SMR protocol later, and even my all authors will be also happy to talk about it. So inherently, we are assuming no threshold setup because we want efficient reconfiguration friendliness. And what we want such a SMR to achieve is that it should be a quadratic complexity SMR, but in every epoch, some node will propose a linear size vector. And in every epoch, we want to make sure that all the nodes commit to at least ON size or linear size proposed value from some node. It's important to see that they are not exactly the same. And in fact, we don't worry about that aspect, as I'll make clear in the next slide. So what property we indeed achieve from in such SMR is that we make sure that although we are sending linear size messages using erasure coding, Reed-Solomon erasure coding, as well as cryptographic accumulators, where the second cryptographic accumulator is the assumption that we require this QSDS setup. We make sure that our protocol remains communication efficient and we achieve quadratic communication complexity. However, there is a trade-off that gets introduced in our SMR. Unlike the other SMR scheme, such as the sync hot stuff and opt sync and others, our SMR could happen that there is a latency in the malicious scenario where the latency of the SMR increases. In our protocol run in epochs of 11 delta each, and each epoch is coordinated by a distinct leader. And in the worst case, when we have continuous T bad nodes, it can indeed happen that a value from an honest node only get committed, or even value from a dishonest node only get committed after T plus 1 epochs. But this is what allows us to go to O of n square. But I want to mention that indeed in our scenario, because we are running on beacon protocol, maybe the protocol has to wait for first T plus 1 epochs to get started. But once you get started, you have pipelining process and you will continuously generate randomness on every epoch. So it's not that we are going to wait on the generating random beacons for every T plus 1 epoch. Once the first T plus 1 rounds are over, we'll continuously emit random beacons of every 11 delta, where delta is the time bound that's complete. It is possible in such a setting that we can avoid this cryptographic accumulator and replace that with a Merkle tree to actually have a protocol which does not require setup and their complexity increases to n square log n. All right, so that was the expectation from SMR, and I wanted to focus on the crypto aspects, what we do, and that's the reason I'm going now into looking at, for the first protocol, we were employing a public verifiable secret sharing, or PVSS. So when we look at publicly verifiable secret sharing, the inherent idea there is that in such a secret sharing, we have a leader, dealer L, who actually want to share a secret S. And because we assume that there are T malicious parties in total, we are going to employ a T degree polynomial here. And such a leader L is going to generate the shares for this particular secret S using this polynomial, which are basically polynomial evaluation. And they actually, in such a system, they take those shares and encrypt those individually for the nodes. So share for the node 1 will be encrypted with the public key for the node 1, and so on, and generate such a pair or such a vector of encryption. But now, along with that, it also includes a cryptographic non-iterative zero-knowledge proof, which demonstrates that these encryptions are actually encryption to the correct shares, such that all the nodes are obtaining their correct shares. And when we are going to take those, any T plus 1 parties can take their shares and they reconstruct a polynomial, and then the secret from that seems the secret will be same as S that initially the dealer started. And basically this is achieved with the non-iterative zero-knowledge proof. Then and such a vector, which is typically O of n size vector, is broadcasted on such secret sharing protocols. And then every node, they collect their such a vector and then they decrypt their value, but they also verify the correctness of the encryption for all the nodes. And when they say that verification is correct, they accept their share as their correct share. And when that happens, the reconstruction is a simple process where basically every node send their secret share to all other nodes, which is basically all-to-all point-to-point communication of O of n square size to reconstruct the secret. This reconstruction process looks very similar to the threshold signing process or threshold signing distribution process that we saw earlier in the system. So the key challenge here, or key task here is this broadcast of size O of n. And the aim will be now, how can we utilize our SMR, which can take such an input and run that through the SMR process to obtain to make sure that we perform the secret sharing engine. So that gives rise to the idea that we can employ towards generating random beacon protocol. And we start with the GRAND paper here, where we employ a publicly verifiable secret sharing scrape by Costudo and David recently. And this scheme indeed comes with interesting computational savings, which were also helpful to us, and certainly the prominent publicly verifiable secret sharing that we employ in such a setting. So the idea here will be in every epoch, a current leader actually shares a new random value as their commitment to generating random beacon protocols. And at the same time, we are going to perform the reconstruction for the value that is proposed by the same leader some round when it was the leader previously, and that's the value that we reconstruct to obtain the value RR. And we just don't use that value directly by itself, because that means that particular leader can predict this value and basically go against the unpredictability attack. But instead, what we do is that we take the previous PVSS -1 randomness. In this slide, assume that F is equal to T, and append them, and then apply the hash function on top of that, which is random oracle hash, to obtain the new value of our here. So in every epoch, the idea is that we start running a state machine replication for the PVSS vector for a new value, and at the same time, we reconstruct the value for the same leader which it has actually committed in the previous. And the process such continues. Basically, we show here the red arrow NQ in one round, and when that same leader LE becomes the leader later, we are going to remove it. And we also make sure that for the intermediate round, all the leaders were distinct and that they're all at least other T leaders which are coming. So in such a setting, indeed, because the nodes, we want to make sure that a node doesn't know when their value will be made public. And we also make sure that we take input from at least T+1 parties. So at least for one of those input will be not known to the adversary. So they cannot bias the input to the system. But it is also important to make sure that it remains unpredictable to the adversary to long run. If we use a round robin protocol, the inherent idea for the adversary will be once it hits the T node for the adversary can predict the value in T epoch in advance for what that will be emitted from the system. So we on purpose make sure that we introduce some randomness into the process of leader selection, so that we select the next leader using the randomness that is generated from the current beacon. At the same time, we make sure that a leader doesn't get repeated for the next T round. So we use a leader. Once that leader was employed, then we are going to put that in a second queue, and then just use only the N-T leaders which have not been used in the previous T rounds to pick the next leader from there on. And for such a setting, we can see that an adversary can predict, given the function that I show here, if X round in advance with a probability that reduces in actually 2 raised to -X, which is precisely when you look at this F choose X divided by N minus F raised to X value, it turns out that that's actually always less than 2 raised to -X. So an adversary cannot really efficiently always predict the setting, and based on whether my N is significantly bigger than the security parameter or not, the number of rounds that I say I don't have unpredictability could be resulted to the kappa rounds, where kappa is the security parameter. In other environment, we may assume that we have unpredictability up to T+1 round, or value based on the protocol. Such a probability can be envisioned, and accordingly, we can say that an adversary has unpredictability or only after T+1 round or something. But even in such a setting, it can always happen that a lucky adversary can predict the values for T+1 round if it turns out that all the nodes that turned out to be coming afterwards are the nodes that are controlled by the adversary. And in such a setting, indeed, they can't go beyond T+1 round, but indeed in such a setting, we want to make sure that we achieve unpredictability even in such a setting so that every value that is outputted remains unpredictable in. And then how can we solve this problem is where we move from our protocol 1 to protocol 2. But maybe one approach could be we run such protocol and run n instances in parallel and hope that then because of those n instances and making sure that we follow the random leader selection for all of them with high probability, we'll have at least one honest leader, and that could be sufficient to make sure that we get the unpredictability for every output. There could be several interesting things we can run with the n parallel instances. But the problem for running n parallel instances will be that our complexity now will become n cube. And that's certainly the problem that we like to solve. And that now brings me to the second protocol that I want to explain, which is B-RANPyTer protocol. And here we go for verifiable secret sharing that rather than publicly verifiable secret sharing as the starting point. So what's the difference between verifiable secret sharing and publicly verifiable secret sharing? Maybe the simplest thing is we do not include zero knowledge proofs to provide correctness that we are doing secret sharing. Instead, we go for the interaction. That's the most simple way to look at it. And we look at a bit more detail and also look at the schemes that are prevalent in such a setting. So when we look at the verifiable secret sharing, here the idea is that dealer L again take a secret and actually put that as a constant term for the polynomial of degree such D. It then generates and broadcasts commitment to all the shares. Important to see difference here is that we don't go for encryptions here, but we instead go for the commitments to the values. And then actually rather with the encryption, the advantage would have been that the nodes can just decrypt and obtain their shares. Now we have to rely on private channels, which are point-to-point channels between the dealer and all other nodes to send those shares individually to those nodes. Okay, because we are replacing encryption by commitment here, it is possible that although we are committing the complete polynomial, which is which has degree t or number of evaluation which is O of n, still we can employ polynomial commitment schemes to make sure that the broadcast size is only constant, in particular O of 1 in such a setting. However, because we do not have any kind of a zero knowledge proof involved in such setting, it can be possible that a malicious leader sends incorrect values to the node. And in that case, traditionally for the verifiable secret sharing, the idea is that nodes publicly complain about incorrect sharing that they receive. And it can very well be the scenario that even when those values are correct, but a malicious receiver itself can just incorrectly blame a correct sender. That's certainly that can happen. And then idea is that the dealer, when it receives such complaints, is supposed to take care of those complaints by just publicly sending the share, which should be verifiable for the commitment that are sent. So dealer just saying, okay, here's the value. If a complaint is coming from malicious node, there is no new information that is getting known to the adversary. So there is no harm that get caused even when the dealer open up such values. Okay, and the reconstruction here for VSS remain exactly same as the publicly verifiable secret sharing, which is again O of n square, all-to-all communication. All right, so how typically this process works, and that I want to just explain with the scheme called Pedersen VSS, which is a very prominently known scheme. So the idea typically is that, okay, I have my, so idea typically is that the nodes first, here our leader or the dealer is node P1, who actually send individual shares to the nodes privately and broadcast commitment to the broadcast protocol. Here for simplicity, I'm showing with the broadcast model where we'll replace that with the state machine replication later. And then when some nodes, if they have any complaint to make, they basically send those messages that those node post messages, whether they're okay with such things or not. if if all nodes say that they receive correct messaging, and if that get published on the broadcast channel, the protocol stop immediately because there is nothing wrong in the protocol. So the protocol continues to the next epoch or whatsoever. However, if there are some complaints that get posted in this round 2, then inherently we require third round where this particular leader P1 is supposed to open those values publicly and send those on the broadcast channel. That's a typical flow for such protocol. This protocol required 2 rounds of broadcast in optimistic case, and in pessimistic case 3 rounds of broadcast. In fact, one of our earlier research, we showed that 2 rounds are necessary and sufficient to achieve it. In particular, this particular protocol, indeed, we could in principle require 3 rounds, but that's less of a problem for us. The bigger problem for us is that in this protocol, as I'm showing with this thick black arrow over here, let's say there are F complaints that a particular leader achieved, it has to actually broadcast the messages which are size O of F. And if we want to make sure that we achieve unpredictability that we aim for and that we run multiple instances in parallel, the challenge here will be now this communication that we are sending on such arrow will get also multiplied with those parallel instances that we are running. How we run those parallel instances, I'll come with, but that's a challenge. This arrow that we see over here is a thick arrow, and that's a problem for us. Okay. On the other hand, the arrow that I'm showing for the commitment is a thin arrow over here, because those commitments, we could employ the polynomial commitment and make sure that they're only constant. All right. So then that's a problem we have to solve. And what we do is that towards solving this problem, we come up with a improvised scheme, which is beneficial for us and which can be useful for the batch VSS in general. Here, the idea is that rather than sending complaints on the bulletin board or the broadcast, we'll assume that those complaints get sent all to all the nodes. And then basically, whenever there are complaints, we just send those complaints to all the nodes on point-to-point links. And then because there could be issues where the malicious complainer only is complained to other node, but not to the dealer, we have a forward blame round where all these complaints get forwarded to the dealer. And then dealer is supposed to resolve all those complaints by opening the shares for them. And if all the complaints are resolved for individual all honest nodes, they are supposed to say, okay, good job certificate to the dealer. And they can be sent to the dealer who then posts them on the broadcast channel, or they can be directly posted on the broadcast channel by the individual nodes by themselves. And that's the approach we come up. The key advantage here is that we avoid opening the complaint share on bulletin board or on the broadcast channel in such an approach where they only get communicated on point-to-point links, and only confirmations are the one which goes to the bulletin board. And we do that to make sure that the whole process that we perform, even when we run n instances of them together, the complexity of the broadcast usage still remain linear in the number of users. So that's the approach we go for using this IVSS scheme. And here is a comparison in precise words. So if you would have using the EVSS, which is the efficient VSS, which basically Pedersen VSS with polynomial commitments, that required the bulletin board access if you're running n instances of size n. So the idea here will be, I'm a user and or I'm a leader. I'm not only doing one secret sharing now, but I'm doing n secret sharings. In that case, the complexity of the things that get pushed on the broadcast channel or state machine replication in that setting are of the size actually O of Fn, where F is the total number of failures in the system. However, when we go for the IVSS, we make sure that it only remains n and not Fn. And that immediately provides us the improvement that we are aiming for, because the use of SMR could be only again for the size O of n, and then we can use the SMR appropriately to get the O of n square complete. However, I haven't explained yet that why do we go for such a batch of size n. And the idea is that I want unpredictability immediate. How can I achieve unpredictability immediately? By making sure that I'm using input from T plus one party. So, or n party, if all of them are available. So what can be the simple idea? The idea is that if we use such a batch sharing, and in every round, every node share n values, such that those n values will be employed for different sharings or different reconstruction later. So a node perform n sharings, and later the idea will be whenever we want to actually use those sharing to generate the values, we are going to take input from all n parties, if all are behaving correctly, or n minus f parties, where f are the parties which are misbehaving. We take input from all these parties that we have collected so far. And in fact, we generate such a matrix so that we'll always have enough such shares available. So we always have a buffer of size t plus 1 available to us. And we'll just take the value from that buffer so that we get input from at least t plus 1 parties. For the secret sharing, we combine those, we homomorphically add those, and reconstruct those values for generating the random beat. So the difference here, why we can do here for VSS versus why we can't do over PVSS, is that inherently in the PVSS, individual verifiable secret share, publicly verifiable secret sharing required O of n. However, here in this protocol, we can run a batch and still achieve the same complexity. And that allows us to make sure that we collect T plus 1 share from different parties towards generating unpredictable randomness in every epoch. Again, similar to the previous thing, even when the failure occurs, we make sure that in every epoch, we are going to reconstruct the values that we want. One minor point, yes?
I'm just wondering if we can pause. I know you're still unpacking a lot of this, but we might have to lose some folks in about 10 minutes on the hour. So I'm wondering if we can pause and see if there are any current questions that folks want to ask.
Sure, or I can also probably just give the brief. So I'm also coming to the end of the discussion. Maybe I'll just take 2 minutes and then we can open up for the questions.
Okay, that sounds great.
Okay. Yeah. So the idea is indeed everybody sent us a vector, and we use individual values from this vector in each round for this party P1 to keep on using that to generate the random. So indeed, I'm coming to the end of the talk. We have implemented this protocol in Rust. And although the complexity for DRAND as well as our protocols are the same asymptotically, and actually, if we remove the asymptotic and look at the precise constant, DRAND should be more efficient in terms of computation at least, and also in terms of communication. There, because of the efficient library that we built in the Rust, we were able to see the better performance in general. Our aim was always that we want to make sure that we remain O of n square and bring the performance as better as we can to DRAND. But as it turns out, at least because of the efficiency of the underlying Rust library that we built, and actually I should thank my student Aditya Pert for all his nice effort, and you should indeed access this libchatter library. We were able to get performance which is comparable or better than DRAND Piper in some scenarios. However, certainly if DRAND start using efficient networking libraries, the performance for DRAND also will improve, no doubt. All right. So I want to briefly talk about something that are upcoming. So for sure, the challenge with our protocol is not always quadratic. So we have already overcome that challenge by using interesting PVSS improvement that are coming up. This last 2-3 years have been very fruitful and active in terms of the research for distributed key generation as well as random beacons, and we are able to use cryptographic ideas to actually make sure that we have always quadratic communication complexity protocol. And we also made sure that our protocol become optimistically responsive so that this 11 delta epoch that we had could be reduced to network speed when the protocol is and the network is ideal. And it's upcoming work by us. So keep an eye on that. I also wanted to talk about what's happening in this field. So one of the prominent protocols I want to talk about is Pert, which is where the same problem in the similar setting with the reconfiguration friendliness is considered now for partial synchrony. And this is work by Saurav Das, Lindgren, and others from UIUC. And final thing where I want to end my discussion is that indeed this random beacon protocol should be considered in settings, possibly in the post-quantum environment, as well as in the unconditional settings, if you want to make sure that we do not require any cryptographic setting that is required. I want to add here a practical aspect that unconditional protocol, because they does not involve using heavy cryptography, we typically find perform much better when especially in the setting requiring because working on computationally less efficient nodes. So something that can be interesting to consider as well. And with that, I'm coming to the end of my slides. The takeaway I want to take here, consider here is that I think when we are building protocols on the internet, but we still want a 49% advantage, and we see indeed synchrony working in such setting, assuming broadcast channel is indeed not an ideal choice, I find. In fact, we should try to incorporate and make sure that we build protocols so that they work in point-to-point setting in such environment. We observe a difference between random beacon protocols and distributed key generation, which is pipeline versus one shot, and that allows us to take and make sure that we get a quadratic communication complexity protocol that does not require a threshold size. All right, yeah, with that, I'm coming to the end of my discussion. I'll be very happy to have questions.
Great. Thank you so much. Really appreciate that talk. And yeah, I want to open it up to questions. I know some folks might need to leave soon. There was a question in the chat from Nicola. Did you want to hop in with that?
Yeah, it was some time ago. So when you were first presenting, I'm not sure it was G-Run Piper or the first one. I'm not sure which one was it, but yeah, you talked about the leader. We don't do round robin because otherwise the attacker can predict when it's going to become leader. And just a question: what happens when he knows he's going to become leader? What can you do? If anything? Yeah, is there any specific thing that it can do, or just?
Yeah. Very good question, right? No. So indeed, the one thing it can do is it knows the randomness that is committed to. It cannot change it, but it can know now what will be the value that will get predicted after 11 delta. And it can slow down the process for other nodes so that they only get to know the value little later, while on the other hand, he knows the randomness that's going to get emitted immediately.
Okay, so he knows the value immediately, but the rest of the honest nodes will know it only later on.
That's in the same epoch, but little later.
Okay.
And it is certainly different. I mean, just to mention that it's the same thing can also happen in particularly any kind of threshold reconstruction, also in BRAN Piper or in DRAN. But the difference there is only one round, while here it could be multiple rounds. That's the difference.
Yeah. Okay. Thanks. And I got another question if nobody has one. Also, like on IVSS, just to make sure I understood, the gain here is because on IVFS you still push the nodes on the bulletin board, right? So this is O of n, right?
Yes. So
where is the gain compared to the 40? Is because we don't require n of f, it's just O of n?
Yes. So in a standard VSS, you have to, let's say I get F complaints, I have to put those F shares on the board. So that O of F on the broadcast. And if I'm running such N batches, that becomes NF.
Yeah.
Here, we make sure that process completely happens in these point-to-point channels. And point-to-point channels, you see with a very particular pattern. I mean, I could not go in all details, but the idea is when I use all-to-all channels, we are always going to use erasure coding to make sure that we get O of n squared, although the inputs are actually size O of n. And if you see these all-to-one and one-to-all, they are O of n. So we don't worry, we still remain O of n squared. So
here, the vote you get O of n for one run of IVSS. If you do n of these in batches, you get O of n squared.
Yeah, so yeah, indeed. So for simplicity of description, I show that here vote can in principle go to broadcast. You can very well just send those votes to the P1 who collects them and then combine them and just send one O of n size broadcast on the broadcast or SMR.
But
so
doesn't that assume...
so the final final message is final black lines that you see here. If you see on my cursor, I don't know, probably my cursor is visible, right?
Yeah, I'm seeing your cursor, yeah.
Yes, so that can go to P1 and then P1 broadcasts the O of n.
But if you do this, don't you assume a new trust assumption on the leader if you do this?
No.
Like you can remove some votes or whatever?
If the leader doesn't do that, then basically all his sharings will be discarded, right? So we don't make any new assumption.
Okay.
So for n batched VSS, this certainly is the interesting approach that we see.
Any other questions? Yeah, Nicola, more?
Yeah, just one last one. You didn't, or maybe I missed the part where you talked about, but you mentioned at the beginning easy group membership change, like easy, like I call it easy resharing, but here how do you group changes?
Exactly. So it's certainly the complete discussion by itself, but the idea, I can try to give brief answer towards that to make it somewhat clear. So the idea is that whenever a new node get added, it's not that immediately he becomes part because he will not have information available. So the new node get added, and for such a new node, we start sending them sharing from now this round onwards. And in T+1 rounds, he'll be ready to become part of the system. When we are throwing out an old node, the idea is simply because once we find out a node is malicious because it did not perform the sharing, which is required, we immediately discard such a node so that we don't have any problem after T+1 rounds again. So the idea is that the new node get added for T+1 rounds, he keep on collecting information, and then it becomes active part because it has now enough vector available of this kind to continue to help the system to run.
I see. Thanks. Yeah, makes sense.
Yes. So the aim there is the process remains O of n square, and we continuously generate the beacons at the same rate, and we don't have a hiccup of size n cube of n raised to 4 because we have to now update the system and how we do it. Removal is even more easy. We just discard if once we find out a node did not perform sharing. Okay, I see chat window there. Okay. So Jorg had a question probably similar to it.
Yeah. Are there any other questions from the audience?
Okay, one last thing, then I stop really. The implementation, so you used a real state machine replication library, or did you implement your own, or what did you do?
So because state machine replication, we come up with the protocol. So there was no protocol available, right? So we implemented from there.
Okay.
And indeed, I guess certainly you is one of our audience, and we'll be happy to discuss more in detail, possibly to consider that you could be possibly who is interested in that. And probably, I guess, I don't want to really take complete credit. So Aditya, my student who implemented this completely, and he indeed see that DRAM's performance could be improved. So putting it this way that even with the new protocol that we are coming up with, the idea will be DRAM because assume the distributed key generation setup. Inherently, the threshold signature sharing could be made efficient, and I think performance can improve. And this Rust-based implementation possibly could help in that direction.
Yeah, for sure. Yeah,
so we also implement our own SMR and our own public key cryptography. That's it.
Awesome. And is this repo on the paper?
Yes, it will be. So I'm pretty sure we included.
Okay. That's because I cannot click on the slide, so that's why.
Let us know. If there's any concern, do let us know. No, so if you look at the ePrint version, probably that was old version, so it does not have implementation. So we can forward it to you.
Yeah, with pleasure, because I don't want to type the long name.
No. I think ePrint version probably does not have the library, but yeah, the conference version will also come online very soon. But we will also update ePrint version for sure with the latest number.
Thanks for joining, everyone. If you have suggestions for a future speaker, or if you'd like to present your own research, please email us at research@protocol.ai. Sign up for our mailing list in the footer at research.protocol.ai to receive monthly talk announcements, funding opportunity announcements, quarterly newsletters, and any other types of emails that you specify you'd like to receive. Please remember to like and subscribe and share this video. Thanks for joining, everyone. We will see you next time.